Hello students, welcome to the session. Now in the last session we have discussed all these points. I think you might have understood. The most important assumption I'm telling you in the interview point of view, it is very important. The first important assumption is what? The system is stable, given system is. Second one is what? The given system is assumed to be in steady state, is operating in steady state until the disturbance takes place. That is why t equal to 0 minus conditions and t equal to minus infinity conditions are same. You understand all of you, okay? So that is why sometimes in the exam he will be asking you 0 minus conditions. In the exam he will be asking you minus infinity conditions. Both are same. Why both are same? Strictly speaking, they are not same. But if you want to really carry out the transient analysis, definitely these assumptions must be made. Otherwise, your entire transient analysis is wrong. You understand all of you, okay? So that is why it's very important in the interview point of view. 0 minus conditions are same as minus infinity conditions. But 0 plus conditions are not same as plus infinity conditions. You understand all of you, okay? Well, now let us look at how do you find the conditions, because in the exam he might be asking you 0 plus, current at t equal to 0 plus, current at plus infinity, current at minus infinity. Of course, minus infinity if you know very well, then you also know the 0 minus according to this particular condition because of the assumption. Okay, so let us look at, we need to know how to calculate, okay, how to determine those values. We just calculate them and let us look at. Remember in the exam when he's asking 0 plus, then you are supposed to construct 0 plus equivalent circuit. Yes or no, all of you? When he's asking plus infinity conditions, you are supposed to construct plus infinity equivalent circuit. If you are asked to find 0 minus or minus infinity, of course both are same, then we need to know what is minus infinity, okay, equivalent circuit. Okay, so we need to be in a position to construct an equivalent circuit for all these conditions. Okay, so let us see now. Let us see now. T equal to minus infinity or t equal to 0 minus. What does it mean? It means that, what does it mean? It means that, okay, before switching operation, steady state, yes or no, all of you? We assume that the system is in steady state until the disturbance takes place. Therefore, both are same. Now, under steady state conditions, the equivalent circuit, switching operation is not happened. Okay, but you have three elements. One is a resistor. How the resistor will behave? It will behave like resistor only all the time. Okay, how the inductor behaves? Inductor behaves like what? Short circuit. Yes or no? Short circuit. Capacitor behaves like what? Open circuit. Capacitor behaves like what? Open circuit. Yes or no? This is how you need to draw the equivalent. For a given circuit, you must replace all these elements by the respective equivalents. R remains. R inductor becomes short circuit. Capacitor behaves like what? Open circuit. Physically, there is an inductor, but behaving like what? Short circuit. Physically, there is a capacitor, but behaving like what? An open circuit. Okay. Now, T equal to plus infinity equivalent circuit. That means what? This is steady state. This is steady state after switching operation. Yes or no, all of you? This is steady state after switching operation. Now you have resistor remain resistor. Yes or no, all of you? Inductor behaves like what? Inductor behaves like what? Again, short circuit only. There is no difference at all. Then you can ask me, sir, what is the difference between these two? Yes, there is a difference. Here before switching operation, whereas here is what? After switching operation. Definitely the circuit characteristics will change. Before switching operation means before disturbance. Okay, and after switching operation means after disturbance. Therefore, the circuit characteristics will change. Understand all of? But the equivalent elements or equivalence of the individual elements will remain same, but overall circuit will change. Yes or no, all of you? Okay. Therefore, inductor behaves like a short circuit. Capacitor behaves like what? Open circuit. That's it. Okay. So please note down. Now, out of 0 minus, 0 plus, minus infinity, plus infinity, except 0 plus equivalent, we are able to draw here all of them. Yes or no, all of you? But for 0 plus conditions, we need a special strategy. Understand all of you? Okay, that we will discuss later. First, you note down this quickly. Please note down that quickly. Let's see that. Let us see that. The first one is, I go with the resistor first, okay? I go with the resistor. So please put the heading here. Initial conditions. Initial conditions in RLC elements. What do you mean by initial conditions? T equal to 0 plus conditions. Yes or no, all of you? We already defined what is initial condition. All T equal to 0 plus conditions are called initial conditions in our entire networks class. Yes or no, all of you? There. Resistor. Resistor V of T or VR of T, let us say. This is IR of T. Okay. IR of T is equal to VR of T by capital R. IR of T is equal to VR of T by capital R. From this expression, we can understand that clearly when voltage changes with respect to time, then the current may also change with respect to time. If voltage changes instantaneously, its corresponding current may also change instantaneously in proportion to the voltage because R is constant. I is directly proportional to V, and vice versa. Voltage may change instantaneously when current changes instantaneously. Therefore, I can say both IR of T and VR of T may change instantaneously, or abruptly or suddenly. They may change instantaneously. Yes or no, all of you? Let me write it clearly. Instantaneously. Okay. Now, that is why we can say IR of 0 plus may not be same as IR of 0 minus. VR of 0 plus may not be same as VR of 0 minus. Hope you understand the point. They may change instantaneously. What does it mean? They may change instantaneously means whatever you found 0 minus conditions, okay, the 0 plus conditions may not be same as 0 minus conditions. That means you have to separately calculate it. Okay, even if you know 0 minus conditions, there is no use at all. You have to find 0 plus conditions separately. Second one. What is the second one? Let us take now. Okay, inductor. Now let us say this is VL of T. Now say this is IL of T. Okay. You can say VL of T is equal to L d IL of T by dt. We already discussed the characteristics of an inductor from this particular expression, that current through inductor may not change instantaneously. Hope you remember that, all of you. IL2 minus IL1 by T2 minus T1. In 0 time, you may not change from 2 amperes to 5 amperes, okay, because to change that quantity you may need infinite voltage. Infinite voltage in 0 time is called ideal impulse voltage, but this thing may not be practically possible. Yes or no, all of you? Okay, that is why from this expression we understand that IL of t or IL of t may not change, okay, may not change instantaneously. Write down all of you, instantaneously, may not change. Let me write clearly, may not change instantaneously. So what does it mean? IL of 0 plus is equal to what? IL of 0 minus. So from this expression we understand that, okay, it may not be practically possible. So ideally speaking, when the voltage across the inductor is finite, then current through inductor, okay, may not be possible. That is practically speaking. I'm sorry, practically speaking, when the voltage across the inductor is finite amount, okay, the current through the inductor may not change instantaneously. But ideally speaking, because all our circuits are ideal, in our circuit analysis, we made a first assumption in the beginning of the entire network theory. What is the assumption we made? The given elements or the given circuit is assumed to be what? Ideal. So under ideal condition, if it is really infinite, nothing but in 0 time, it is ideal impulse current, ideal impulse voltage. When ideal impulse voltage is given, current through inductor may change instantaneously. All these things we discussed in the case of inductors and capacitors. That is why I told you at that point, the characteristics of the inductors and capacitors will help you a lot in transient analysis. Now the entire transient analysis will move around these 2 points only. Current through inductor may not change instantaneously. Voltage across the capacitor may not change instantaneously, provided voltage across the inductor is finite and current through capacitor is finite. Otherwise, they may also change instantaneously. That's a very, very important point I'm telling you. Okay, but voltage may change instantaneously. May change instantaneously. VL of 0 plus may not be equal to VL of 0 minus. So I told you already that why we should use may, why we should not use shall change, shall not change, will not change, does not change. I told you not to use all those words. Always use may or may not. I gave a clear explanation in the case of inductors and capacitors. Okay, so please refer once again. Why should we use? Okay. Now note. In the case of inductor, okay, what is this actually? Flux, right? Phi of t, L, I of t. Once again, this is V of t, right? Or VL of t. Once again, I'm writing. Okay, I'm just elaborating. Already we discussed these points, but better you document all these points at one place so that when you refer the notes just before the exam, it will help you a lot. Okay, so please note on that. So what is the first point? If VL of t is finite, if VL of t is finite, then IL of 0 plus is equal to what? IL of 0 minus. It is also phi of 0 plus is equal to phi of 0 minus. It may not change instantaneously. Okay. Second point, if VL of t is infinite, nothing but what? Ideal impulse. Ideal impulse. Then IL of 0 plus may not be same as what? IL of 0 minus. That's it. So very, very important point. Okay. Now let's go for the capacitor. Please note down that up to that particular point, I'm going to write the capacitor here. Meanwhile, I just erase it. Please note on that quickly. Please note on that quickly. I will go with the capacitor, initial conditions in capacitor. Initial conditions in capacitor. Please note on that. Coming to now, third one is a capacitor. When you take the capacitor, Vc of t, right? This is Ic of t. Of course, you have a charge Qc of t or Q of t. Now, Ic of t is equal to C dVc of t by dt. We discussed it very clearly in the case of characteristics of capacitors and inductors, okay? Capacitors. C into Vc2 minus Vc1 by T2 minus T1. This is 0. This is 2 volts to 5 volts. Then how much actually you require the current? What does it mean? Tell me all of you. If you want to change voltage from 2 volts to 5 volts in 0 time, you require infinite amount of current. That is nothing but ideal impulse current, which is practically not possible. That is why we said Vc of t may not change instantaneously. That is nothing but Vc of 0 plus is equal to what? Vc of 0 minus. But current through capacitor may change instantaneously. Please write down that, all of you along with me. You already learnt all these things in the case of inductor capacitor. Okay, so let us not wait. Please take down along with me. May change instantaneously. That is, Ic of 0 plus is not equal to Ic of 0 minus. May not be equal to Ic of 0 minus. But you can keep it a note. If Ic of t is finite, if Ic of t is finite, if Ic of t is finite, okay, if it is finite, what will happen? It may not change, right? Okay, so let's write that. If Ic of t is finite, then Vc of 0 plus is equal to Vc of 0 minus. This is also same as what? This is true for even Q of 0 plus is equal to Q of 0 minus. Just now we have seen flux of 0 plus is equal to flux of 0 minus. Okay, phi of 0 plus may not be same as, is not equal to phi of 0 minus. Please write down that point also. Okay, in the earlier case, if Ic of t is infinite, nothing but what? Ideal impulse. Ideal impulse. Yeah, there are some special problems involved on all these conditions. That is why I am discussing in detail. Okay, one should know all this. To solve those special problems easily, in 1-2 steps, you can solve those special problems. So Vc of 0 plus may not be same as Vc of 0 minus. So it's nothing but Q of 0 plus may not be equal to Q of 0 minus. That's it. It's a very, very important point. So these are all the initial conditions how we evaluate, okay, in the case of inductor, capacitor and resistor, 0 plus conditions. From this, we can, okay, frame a table which is so much useful to you in solving the problems. Okay, that we'll discuss now. Please, I think all of you noted down this. Quickly go ahead with that. Please note on that. I think you have done this part. Okay. Hope you have noted down this part also, right? So one should really remember all these things. Should not get any doubt again. I'm just going to give a table now. So let's frame a table which is very interesting here. Very, very interesting here. A table, serial number. Let me take here serial number, element at t equal to 0 minus. Okay, of course, minus infinity both are same, right? Or t equal to minus infinity. Equivalent at t equal to 0 plus. So what is the element at t equal to 0 minus? That means before switching operation, what is the original element? It might be resistor, inductor, capacitor. And what is the equivalent? If you know t equal to 0 minus conditions, just now we have seen 0 minus conditions. If you know very well, probably you can construct t equal to 0 plus easily. Okay, so let us look at that. The first one is resistor. So current through the resistor and voltage across the resistor may change instantaneously. Yes or no, all of you? Even if you have 0 minus, then 0 plus conditions may change. Both are not same. Both current and voltage. The ratio is same again. Therefore, the equivalent of that resistor will remain resistor only. There is no change in that. Now, inductor. What is the inductor at t equal to 0 minus? Assume that the current flowing through this particular inductor is 0 ampere. You can ask me, sir, how do you know that the current flowing through that particular inductor is 0? No, I may not know. But if I find that current through the inductor at t equal to 0 minus, I have a mechanism to find t equal to 0 minus current. Is that all of you? How do I find? Tell me, all of you. Okay, we have an equivalent circuit for t equal to 0 minus. How do you visualize t equal to 0 minus equivalent? At t equal to 0 minus, switching operation is not taken place. Resistor remains resistor. Inductor behaves like a short circuit. Yes or no? Capacitor behaves like open circuit. Now current through short circuit, physically what is there actually? Inductor only. But behaving like what? A short circuit. Physically inductor is there. So current through short circuit is nothing but current through inductor. Understand? Voltage across the open circuit is nothing but voltage across the capacitor. Yes or no, all of you? Okay. Therefore, I find the current through the inductor. Now that current might be either 0, don't know, or else it might be non-zero. There are only two options, right? Either 0 or non-zero. There is no option for infinity. Yes or no, all of you? Infinity current may not flow. If infinite current flows, I told you already, that happens only when there is a violation of Kirchhoff's voltage law, which is an invalid circuit. Yes or no, all of you? So you have only two options. One is 0 current, the other is a non-zero current. So let me take first with 0. Then second, the other case, I would like to take non-zero current, then we will see what will happen. Now current through the inductor at t equal to 0 minus, IL of 0 minus is how much it is found to be? 0. I have drawn the circuit, equivalent at t equal to 0 minus, and I found current through the short circuit, nothing but current through the inductor. I found that 0 ampere. Then current through the same inductor at t equal to 0 plus is also 0, with an assumption that voltage across the inductor is finite. Hope all of you remember. So this entire table is valid only when you assume that current through the voltage across the inductor is finite and current through capacitor is finite. With that assumption only I am drawing here. Understand, all of you? Okay. So therefore, here current through inductor may not change instantaneously. Here it is 0. Here also it is 0. When it is 0, then it is acting like what? Current 0 refers to what? Open circuit. Current 0 refers to what? Open circuit. Therefore, it is acting like open circuit. It's a very, very important observation. Okay. Third one is inductor. Current is found to be IL of 0 minus is some I naught. I don't know whether it is 2 amperes or minus 5 amperes or minus 20 amperes. Might be anything. It all depends on the circuit. You give me a circuit, I'll construct T equal to 0 minus equivalent. Then there I find the inductor is replaced by the short circuit. What is the current through the short circuit? The current through the short circuit is found to be I naught. It might be any value. Then current through the inductor at T equal to 0 plus is also same with an assumption voltage across the inductor is finite. If it is same, means the same current should flow. Yes or no, all of you? At a particular instant of time, if you know current, okay, can't you replace that element by an ideal current source according to substitution theorem? Yes or no, all of you? Based on that, now I am replacing the inductor, okay, by an equivalent ideal current source with a parallel inductor model. Remember, this is an inductor. This is an inductor, but I am replacing it by, because I know the current flowing through the inductor is found to be I naught. I am placing here I naught with a parallel inductor model. Remember, all of you, this is very, very important. There are some special problems involved, okay, in all these equivalents. Okay, this is an inductor. Physical inductor is available. Physical inductor is available. Now, fourth one is capacitor. Capacitor. Similarly, capacitor. Okay. If you know the voltage across the capacitor is Vc of 0 minus is found to be 0. Sometimes 0. Or sometimes it might be non-zero value. Definitely not infinity. Voltage becomes infinity only when there is a KCL violation. Yes or no, all of you? Okay. Then that circuit is called invalid circuit. So we are not working on invalid circuits. We are working on valid circuits. Look at this. Now, the voltage across the capacitor was 0 at T equal to 0 minus. Then it is also 0 at T equal to 0 plus. Voltage 0 refers to short circuit. Therefore, the capacitor is replaced by the short circuit. So if you want to construct T equal to 0 plus equivalent circuit, you must maintain all these things. But all these things happen only when you know the conditions at T equal to 0 minus in L and C. So voltage across the inductor, current through the inductor and voltage across the capacitor are very, very important before switching operation. That means T equal to 0 minus. If you know them, then only it is possible to construct T equal to 0 plus equivalent. Understand all of you? Okay. Fifth one. It's very, very important again. Capacitor with some initial voltage. What is that initial voltage? Okay. Is some V naught, let us assume. Now, you are going to replace it by an equivalent. Maintain the same polarities, plus minus. Maintain the same direction. You remember, all of you, the substitution theorem, we maintain the same polarity, same direction. Now, according to substitution theorem, the capacitor is replaced by, okay, the voltage source. But there is a model, capacitor model. It's very, very important. Okay, this is a capacitor in series. Series capacitor model. What is this? Series capacitor model. So it's a very, very important table. Okay, just note down this. With this table, now we are going to play with our circuits. Okay, so please note down this. So when you want to draw T equal to 0 plus equivalent circuit, you are supposed to remember all these things. Now all these are depending on what? The current through the inductor and voltage across capacitor at T equal to 0 minus. Yes or no, all of you? You decided the open circuit, it is based upon current through inductor at T equal to 0 minus. Decided current source here, okay, it is because of current through the inductor at T equal to 0 minus. All these things are, okay, is possible to draw only when you know the T equal to 0 minus conditions in the case of inductor and capacitor. Please note down quickly. Right. Now let us look at, in the calculation point of view, when we are asked to find 0 plus conditions, we need to follow a step-by-step approach to avoid all the confusions, to avoid all the calculation mistakes. Okay, so let's do that. Step 1, write down here step by step or steps to determine t equal to 0 plus conditions. T equal to 0 plus conditions. Step 1, I think you might have understood by this time, without t equal to 0 minus we cannot proceed. So construct t equal to 0 minus equivalent circuit and find or determine IL of 0 minus and VC of 0 minus. I hope you understand the terminology clearly. Current through inductor, voltage across capacitor. Suppose in the question, if you are asked to find only current through inductor and voltage across capacitor t equal to 0 plus, with an assumption that voltage across the inductor is finite, current through capacitor is finite, then obviously you have the answer at t equal to 0 plus here itself. Yes or no, all of you? Because you know that current through inductor may not change. IL of 0 minus, VC of 0 plus, voltage across the capacitor may not change. So this is possible only when what? Voltage across the inductor is finite, current through capacitor is finite. Otherwise, this is not valid. Okay. So you have to find, irrespective of the question, when somebody is asking 0 plus conditions, then irrespective of the question, you are supposed to, okay, determine current through inductor, voltage across capacitor at t equal to 0 minus. Understand all of you? Okay. Right. Now step 2. What is step 2? Step 2 is, okay, see, this is construct t equal to 0 minus equivalent. But other than current through inductor, voltage across capacitor are asked in the exam. Okay. In order to determine or otherwise you can say, now let's look at like this. Now construct t equal to 0 plus equivalent circuit in order to determine. It's very clear. In order to determine what is that? Other than these two quantities, what are they? IR of 0 plus, VR of 0 plus, IC of 0 plus, VL of 0 plus. Other than current through inductor and voltage across capacitor, if somebody is asking you any question on 0 plus conditions of these quantities, certainly you are supposed to construct t equal to 0 plus equivalent. I hope you understand this. You have 6 quantities, current, voltage of 3 elements, inductor, capacitor, resistor, total 6 quantities, 2 into 3, 6 quantities. In those 6 quantities, the 2 quantities can be determined only from first step itself. But you can go for second step when other than the 2 quantities, what are they? Current through inductor and voltage across capacitor. Other than these 2, you are supposed to construct t equal to 0 plus equivalent. Okay. Now, step 3. There is a possibility for getting higher order derivative terms, the initial conditions of higher order derivative terms. Because you know that, okay, d square plus 3d plus 2 of some I of t is equal to 10. Just now we have seen this example in the last session. Okay, in the last session we have seen that. What did we get I of t totally? Tell me all of you. K1 e power minus t plus k2 e power minus 2t plus 5. This is what we determined. But we already declared that to determine these arbitrary constants we require initial conditions. But what are the initial conditions we have? We can apply, okay, t equal to 0 plus conditions to what? Equation 1. That means I of 0 plus k1 into 1 plus k2 into 1 plus 5. Say this is equation A. But you have two arbitrary constants. For that you require two equations. Yes or no, all of you? For that you require two conditions. So what will you do? You cannot take 0 minus. You cannot take minus infinity plus infinity. It is not possible because arbitrary constants can be determined only from initial conditions. And in our class, initial conditions are nothing but what? 0 plus conditions. Therefore, what we do is, we differentiate equation 1, d by dt of equation 1. If you do that, what do you get, Nana? di of t by dt is equal to what? Minus k1 into e power minus t minus 2k2 into e power minus 2t plus 0. Now apply t equal to 0 plus conditions to this equation. Equation 2. Equation 2. What will you get? di of 0 plus by dt minus k1 into 1 minus 2k2 into 1. That's it. Equation B. Look at this. If you know I of 0 plus, this you can determine either from first step or second step. It depends upon the current, whether it is through resistor or inductor or capacitor. If it is through inductor, you get from first step itself. If it is other than inductor, you have to get it from step 2, but finally you are getting either from step 1 or step 2. Yes or no, all of you? Now, di of 0 plus by dt should also be calculated. This is also an initial condition. So, initial conditions are of two types. One is a non-derivative term, the other is a derivative term. Understand all of you, okay? Since it is a second order system, you got initial conditions I of 0 plus and di of 0 plus by dt. Two initial conditions required because there are two arbitrary constants. If it is an nth order differential equation, you require n arbitrary constant values. Then what are the initial conditions you require? Tell me, all of you. You require I of 0 plus, di of 0 plus by dt, and then what? d power n minus 1 I of 0 plus by dt power n minus 1. These are the initial conditions required. If you know these initial conditions values, then only it is possible to find the arbitrary constants. Yes or no, all of you, okay? That is why, okay, we determine not only the non-derivative terms from here, because sometimes in the exam, you may be asked to determine the derivative terms also, initial conditions of derivative terms. So what will you do in case of initial conditions of derivative terms? Suppose you have, let us say, the resistor and inductor circuit. Anyway, we are going to discuss some problems later, but let me take a simple example here. Say this is a switching, closing at t equal to 0. This is L, let us say, at okay, t, that time t, that is a current, okay, I of t, I'm sorry, here I of t we can say, and this is V. Now let us apply KVL. Now I of t into R plus L di of t by dt, yes or no, is equal to what? V, equation 1. Okay, if I obtain the differential equation using either KVL, in case of parallel circuit KCL, some differential equation must be obtained. And this differential equation is obtained for what? T greater than 0, t less than 0. T greater than 0, because after switching operation, your concern is always after switching operation. Okay, your concern is at t equal to 0 plus. 0 plus is nothing but what? Greater than 0. Therefore, you require a differential equation for t greater than 0. Once you know the equation for t greater than 0, you can apply t equal to 0 plus conditions to this equation or not? Yes, you can apply. T equal to 0 plus, you can apply I of 0 plus. You know already I of 0 plus value from either step 1 or step 2, just now we discussed. And di of 0 plus by dt, you want to find it. V is a known value, L is a known value, R is a known value. Finally, you are able to find this di of 0 plus by dt or not? Yes, you can. Suppose you want to get d square I of 0 plus by dt square. Differentiate this entire equation with respect to t. Yes or no? What will you get then? di of t by dt into R plus L d square I of t by dt square is equal to 0 because it is constant DC source, 0. Now again you apply t equal to 0 plus conditions to it. Already you know di of 0 plus by dt. Yes or no? di of 0 plus by dt. You already know about it. Just now you found in the previous step. So you can easily find okay, L d square I of 0 plus by dt square can also be determined or not. If you differentiate the equation 1, d by dt of equation 1, you will also get by applying t equal to 0 plus conditions to this equation. Got it, all of you? Okay, that means what? If you want to get the higher order differential terms, you must be knowing the differential equations of that particular given circuit in terms of the desired quantities. In terms of the desired quantities, whether it is I of t or V of t, in terms of the desired quantities, okay, using either KVL or KCL. If you know this differential equation using KVL or KCL, then you can play with the differential equation and find the initial conditions of your desired term can be determined easily. Understand, all of you? Let's do that. So step 3 is meant for what? Initial conditions of higher order differential terms. Understand, all of you? Okay? Initial conditions of higher order differential terms can be determined in step 3 only. So you go for step 3 only for that particular sake. Understand, all of you? Okay. Well, now, in order to determine di of 0 plus by dt, I hope you understand this. D square I of 0 plus by dt square, and so on. That means what? The initial conditions, 0 plus conditions of higher order differential terms. Okay. In order to determine this, comma, obtain differential equations for okay, for t greater than 0 using either KCL or KVL, or sometimes both combinations we need to go. Finally, we require a differential equation. How you find that is up to you only. Some people may get it using KCL, some people may get it using KVL, some people may need even both the combination of KCL and KVL. But finally, you require a differential equation for t greater than 0. Why t greater than 0? Because we are interested in t equal to 0 plus. 0 plus is nothing but what? After switching operation, that is greater than 0 only. Okay, so this is how step-by-step approach we need to go ahead with all these things. Okay, okay. Now note down this important steps to determine t equal to 0 plus conditions. This is all just an explanation I gave you to make you understand why we need higher order differential terms. Okay, initial conditions are of two types. One is a non-derivative IV, right? The other is a derivative di by dt, d square I by dt square, and so on. If you have an nth order differential equation, you require n arbitrary constants. N arbitrary constants means you require n initial conditions. In these n initial conditions, one initial condition is a non-derivative. All n minus 1 initial conditions are of derivative terms. Is it clear, all of you? Okay, so it's very, very important. So one should be good at mathematics. One should be really good at mathematics to enjoy these